Okay, we are gonna wrap up the last chapter here. I don't know. We were talking about electrochemistry, I think. Whatever chapter 17-ish, maybe. So we were talking about sort of non-standard conditions, kind of like what we saw today in lab, a little Nernst action equation happening there. So this is the Nernst equation. Again, we use it for sort of non-standard conditions, kind of like the lab we did today. Where you have concentrations that are not all 1 molar. We do need to use this. Again, this is thinking of it like under non-standard conditions. That's the E of the cell, which is our cathode minus our anode. These are our normal guys, our 8.314. Our temperature in Kelvin, our moles of electrons, our Faraday's constant, 96,500. And Q is obviously our products divided by our reactants, again, taking our coefficients as the exponents when we do it. We also saw that basically if we were sort of to hit equilibrium or at equilibrium, okay, I guess at equilibrium would be good. Q would equal K and E would equal 0. So that gives us the other equation that we were using. Looks something like this. And again, it's really just sort of rearranging that equation. And again, that's the one we want to use when we are dealing with anything that involves the equilibrium constant and obviously sort of a galvanic cell or E of the cell. We finished up talking about batteries, which are really just galvanic cells. And we also talked about corrosion of metals, and corrosion of metals is really the oxidation of metals that occur because the metal has a more negative SRP value than oxygen. And again, as we talked about, what that essentially does is make oxygen the cathode and the metals the anode. So all the oxidation occurs there on the metals, and that's basically what corrosion sort of is. And we talked about some ways, obviously, that you can protect against that, like painting, alloying, galvanizing. So some of those things you can do to protect. Any questions on any of those things there? Yeah. Yeah, so you need to know pretty much how a battery is similar and different to a galvanic cell that you would build in the laboratory. That could almost be word for word the question, by the way, just so you know. So that's what you need to sort of know. In terms of corrosion, you need to know kind of what corrosion is, ways to prevent sort of corrosion. That would be like part B of that question, probably. When you put it together, the exam is just like writing itself right now, but that's basically what you need to know. So specifically, I'm not going to ask you, what's like the Duracell reaction there or anything like that, or any of those reactions. So just kind of generality on those two topics we covered at the end there in terms of batteries and corrosion, sort of what it is, how they're similar, obviously, to traditional galvanic cells. Other questions? All right, then what we have left is electrolysis. Good talk. Let's go back. All right, so electrolysis is the process of using electrical energy to cause a non-spontaneous reaction to occur. So when we have a spontaneous reaction that occurs, as we also talked about, we will have a positive value for E of the cell. That would give us a negative value for delta G, and again, should have a larger value for K. And obviously the opposite of that, if we have a negative value for E, that means we will have a positive value for Q, and it'd be non-spontaneous reaction, and we'll have a lower or a low value of K. So we use electrolysis to cause these sort of non-spontaneous processes to occur. For example, if we took water, you can't just, break apart water. It won't just happen naturally. So if you run an electrical current over it, you can basically break water back into hydrogen gas and oxygen gas and do a little balancing there. And that will cause that sort of non-spontaneous process to work. Same thing here, as we can see something like sodium chloride here. When we take sodium chloride, which is salt, it does not spontaneously basically go back to its elements pretty much. So it doesn't go back to sodium metal and some chlorine gas in this particular case. And we can again run an electrical current over it to cause that process to happen. So by running the electrical current over it, it basically will sort of overcome what is necessary for that reaction to take place. So there is sort of a difference in terms of when you run an electrolysis sort of cell to a traditional galvanic cell in terms of what is happening. So for example, here, if we hook up our battery, we're going from our anode to our cathode. So when we make something like sodium chloride and putting it together, when we look at what's happening when we actually do this sort of synthesis reaction, we have 0 for our sodium, we have 0 in terms of oxidation state for our chlorine. When they come together here, +1 and -1 there for our chlorine. And in the case of when we put it together, the one that's being oxidized is the sodium, which would be the anode in this case. And the chlorine here is being reduced as it's becoming more negative, and that would be our cathode in this case. But when we're doing the electrolysis reaction, which is basically the reverse reaction, we're actually going from sodium up here that is +1 to 0, which means in this case, the sodium is actually becoming more negative and it's actually being reduced. And that would actually be our cathode. And our chlorine is going from -1 to 0 on this side, and that is being oxidized, and that would be our anode. So sometimes when people do sort of electrolysis problems, they think of the reaction the wrong way. They think of it as like making the sodium chloride, which your anode and cathode would be switched in that case. So that's why when we come over here, we actually do see our anode reaction, which in this case is actually the chlorine. And the chlorine is going from -1 to Cl2, which again has oxidation state of 0, and is losing those electrons. Those electrons are going to come around to the other side there and be gained by the sodium ion, and will make basically our sort of solidish, liquidish, in this case, molten sodium in this example. So when you have an electrolysis cell, it is opposite in the sense of sort of when you put it together, because you're basically doing the opposite reaction, right? You're kind of doing the decomposition reaction versus the synthesis reaction. And again, sometimes people think of it in the wrong way. Any questions on that? That's also why when we look at something like water here, when we do the electrolysis of water, once again, if we just look at the oxidation states, +1 to 0, -2 to 0 in this case. So in this particular case, it is the oxygen that is going from -2 to 0 that is being oxidized and would be our anode, which is what we see happening here. And on this other one here, it is actually the hydrogen that is going from +1 to 0 that is being reduced, which is what we see over here. So again, that is the opposite reaction that's sort of happening of putting it together, going the opposite way. So if you run electrical current over water, which you could do with like a 9-volt battery and a little bit of wires, and you will basically break apart water into hydrogen gas and oxygen gas. And if you were to collect it, as we see here in this empty spot in the test tube, that is where our gas is, right? So that's our oxygen gas there on the right and our hydrogen gas on the left. Why is there more hydrogen than oxygen? Yeah, it's H2O, right? So twice the amount of hydrogen per oxygen is going to be generated in this particular case, as we can see from our balance equation there, perhaps. Yeah. So in this particular case, what we will collect here is our water. When we do water, though, to actually make this work really well, you need a little bit of extra hydrogen sort of in the water there to help it out. So it's a lot of times acidic water. So sometimes when they do the electrolysis of water in problems, they will not just come out and straight say, you're doing the electrolysis of water, they'll say something like sulfuric acid involved, some type of acid involved. So they sometimes will hide it in problems that it's like the electrolysis of water. So if you see something involving, like you see here, sulfuric acid, or some type of acidic type of solution or something that's added to water, it's going to be the electrolysis of water, and it's really going to be these two sort of half reaction that's occurring here. So when we do electrolysis type problems, there's sort of a few steps that occur. We can use our charge, which is equal to an amp times the time. And an amperage means that it's basically a coulomb over a second, and a coulomb is a unit of electrical charge, if we rearrange that there. So a lot of times you'll be given, you ran this electrolysis cell at a current of however many amps for this much time. So a lot of times what we want to do is take our time and convert it into seconds if it's not there, and then take our amperage, which is really coulombs per second, and multiply them by each other. And that gives us basically the coulomb or electrical charge associated with this sort of cell. And that would take us down to here. At that point, we actually will use Faraday's constant here. And using Faraday's constant, we could go from 96,500 coulombs per mole of electron. The coulombs will cancel, and that will get us down to basically the moles of electron. At this point, this is where the balanced half reactions come into play. The balanced half reactions, which once again, we would have an oxidation half reaction, and we would have a balanced reduction half reaction. We would use our half reactions that are balanced and do really stoichiometry, moles of electrons to moles of whatever we're interested in. And we would use moles of electrons to moles of whatever we may be interested in. And that will essentially give us the moles of what we're looking for, either what's being oxidized or what's being reduced. At that point, you really have kind of two paths that sometimes will occur here. A lot of times you might be interested in how many grams you would produce as a result of this reaction that's happening. So you would take the moles to grams using something like the molar mass. A lot of times, though, you are going to be producing some type of gas. So very commonly, they may want to know the volume of the gas that you're collecting. And that means if you happen to be collecting a gas, our good friend PV equals nRT might pop up. And again, that should be in atmospheres, that should be in liters, that should be moles, that should be Kelvin, and R here, 0.08206 liters atmosphere Kelvin mole. So if you get to this part and you're looking for a volume of a gas, they probably would give you perhaps the temperature and the pressure, and you would be able to solve for the volume at that point using the ideal gas law. So those are the two common sort of end runs on these type of problems, which is you figure out how many grams if it's some type of metal perhaps that you're producing. But if it is a gas, you sometimes will have to, at the end, kind of stick it into the ideal gas law there and solve for volume. Question on that there. Volume obviously would be nRT divided by P in this case, right? All right, so let's take a look at one together. We'll come back to that one, I think, here. Let's do this one. So how much calcium will be produced in a electrolysis cell from molten calcium chloride if the current is 0.452 amperage and it runs for 1.5 hours. So once again, we want to think about what's really happening here. We're going to go from calcium chloride to calcium pretty much metal and some chlorine gas in this case, right? So when we think about what is our anode, what is our cathode, what is happening, once again here, our calcium is going from not 0, but +2 to 0. Our chlorine is going from -1 to 0 in this case. So here we do see that it is the calcium that is actually again being reduced, which means our calcium would be our cathode. I'm going to spit that out. Chlorine is going from -1 to 0, which means it is being oxidized and would be our anode. So in this case, we're going from calcium, going to add a couple of electrons, and that's going to give us calcium here as our cathode reaction. We have a couple of these chlorines here, going to make Cl2 plus a couple of electrons here on our anode side in this case. So those are our two half reactions. I think in the notes they're given to you, but they may not always be given to you. And that is sort of how you can sort of determine what you'll end up with. So in this case, we're going to do our sort of typical calculation here. We're going to take our 0.452 amp, and that basically is 0.452 coulombs per second, as that is what an amperage is equal to. We have our time here in hours, but again, for everything to cancel out correctly, we do need it in seconds. So an hour is 3,600 seconds, perhaps. Yeah. And that is going to be 1.5 times 3,600, 5,400 seconds. So we have pretty much everything that we might want to use here. We're going to start with our time. And this is how long we're running this cell. We're going to use our amperage and times it by it. This will cancel out the seconds, and this will give us the electrical charge that's happening there for our cell, which looks like it is about 2440.8 coulombs. Now that we have the electrical charge, we're going to use Faraday's constant and convert that into moles of electrons. So there's 96,500 coulombs and a mole of electron. So we're going to divide that by 96,500. That's going to give us 0.0253 moles of electrons. Any questions so far? Now that we have moles of electrons, this again is where our balanced half reactions come into play. And we will do really like just stoichiometry, since we're interested in calcium in this case. And by the way, we're interested in the calcium with no charge, right? So the guy that has no charge. When we look at this half reaction, it is a 1 mole of calcium will give us 2 moles of electrons. So we're going to use that just like in stoichiometry here to go from moles of electron to moles of what we're interested in, which is 0.0253 moles of electrons. There are 2 moles of electron for every mole of calcium. Moles of electron will cancel, and we'll divide that by 2 perhaps, gives us 0.0126 moles of calcium. In this case, we are interested in how many grams. So at this point, we would use the molar mass of calcium from the periodic table. That's like a 4008, I believe. And again, that comes from the periodic table and the molar mass. The moles will cancel. And that's going to tell us that if we ran this cell, we're looking at 0.51 grams of calcium would be produced in this case after 1.5 hours that went through. Question on those steps. Now, if I was interested in chlorine as well, like how many grams of chlorine, or maybe I do have a pressure and temperature given to me or something like that, I can figure out the volume. But if I was just interested in how many grams of chlorine gas technically we would produce, we could also just pick it up right here. And we would do the same thing. We would look between the chlorine and the moles there. And that would also be the same relationship in this case. So you would take 0.0253 moles of chlorine, electrons. And we would do our 2 moles of electrons to 1 mole of Cl2. And that would get us basically our same number here, 0.0126 moles of chlorine. At that point, like I said, if you had some ideal gas law information, you could go into the ideal gas law. You could also just get the molar mass of Cl2, if that was the question by some chance. And the molar mass of Cl2 would be 7090. From the periodic table, and that would get you something like about 0.89 grams of Cl2. My guess is probably you would be asked more like the volume there and be given some other information and plug it in. Any questions on those steps there? Variation on this type of problem is they tell you how much you produce and you work your way backwards to figure out how long you ran the cell for, or what the amperage was, sort of working backwards in that calculation. All right, so why don't you try the one we skipped here? We are going to run a current of 1.26 amps is passed through an electrolysis cell that contains sulfuric acid for 7.44 hours. Write the half reactions and calculate the volume of each gas generated. So this is an example, as I was talking about earlier, doesn't mention really anything about water, but you're running it through some sulfuric acid. So that's sort of the key word to tell you that this is the electrolysis of water, basically, that's happening here. When we talk about STP, that's standard temperature and pressure. That's the temperature of, not everybody at once. Yeah. So actually 273 Kelvin. Pressure is 1 atmosphere. Yeah, that is STP conditions. All right, so see what you come up with. So we're going to run this for 7.44 hours, and I'll give you the half reactions there. So we're going to run it for 7.44 hours at 126, looks like. Yeah. What is the volume of hydrogen gas and oxygen gas that you're going to collect in this case at STP, which again is 273 Kelvin and 1 atmosphere. All right, take a few minutes, see what you go. Once again, as I mentioned before, a lot of times they won't mention straight out that it's electrolysis of water. They will mention something like sulfuric acid, some type of acid involved. And then obviously these would be the half reactions that are happening here. So we're going to basically start this problem off very similar to the other one. We have our 1.26 amps, which is coulombs per second. We also do need to, again, convert our time into seconds so everything cancels out correctly. Got a little 3,600 seconds there. That's going to get us 7.44 times 3,600. That's like 26,784 seconds. So we're going to multiply that by really the amperage that we ran the cell by, and that was 1.26 coulombs per second. Our seconds will cancel. Going to get us 3374784 coulombs. Going to divide that by our Faraday's constant so we can finally get it into moles of electrons, which is going to allow us to use our half reactions up here. The coulombs will cancel, and that's going to end us with, we'll go with 0.3450 moles of electrons. Any questions up to that point? So really the front part here is just sort of the work so that you could get it into those electrons so that you then can use your balanced half reactions to finish up the problem. At this point, we're going to start with maybe one to begin with. I'm going to go with oxygen first. So looking at this half reaction here, which is our oxygen, we can see that for every 4 moles of electrons, which is the coefficient, we get 1 mole there of our oxygen. So taking our number of 0.350 moles of electrons, using really the stoichiometry from the balanced half reaction, 4 moles of electrons gives us 1 mole of oxygen. Dividing that by 4. Going to get us something like 0.0874 moles of oxygen. I now have the moles of oxygen here. I obviously have my temperature and my pressure. Once again, you always have R, which is our gas constant. So we can go into PV equals nRT and solve for volume, which would be nRT divided by P. We could put all of our numbers in there. And in this case, it would give us the volume of oxygen would be our 0.0874 moles. our 0.08206, which is our gas constant, our 21, if you like that number better, our 273, which is what STP stands for, and our 1 atmosphere, which is what STP stands for. And doing all that good stuff there. Going to get us about 1.96 liters of O2 here was collected. Any questions up to that point? We also want to know how much hydrogen was collected. So we basically have to do the same sort of step there for hydrogen. So we're going to go into our second half reaction that involves hydrogen and look at the relationship here. There is a 4 on the outside, which means if you multiply the 4 in, you get a relationship of 4 moles of electrons equals basically 4 divided by 2 is 2 moles of H2, which is the same relationship as 2 moles of electrons is 1 mole of H2. So you really could use either one, they'll come out the same. So we're going to pick back up here, though, with our moles of electrons for our hydrogen. So we'll go 0.350 moles of electron. We'll use our relationship, whichever one you want to use there, 4 moles of electrons to 2 moles of H2, our 1 to 2. And we will end up here with 0.175 moles of H2 in this case. So now that we have that, it's the same conditions for our hydrogen. So our volume here would be 0.175 moles. Our gas constant, since I'm running out of room, I won't put the units in there, 273 Kelvin, all divided by our 1 atmosphere. And if we do that there, that's going to get us 0.08206 times 273. Going to get us a 3.92 liters of H2 would also be collected in this case. And if we divide it by 2, that's like $1.96-ish or so. So that's a 2-to-1 ratio, as we would expect here, right, for our hydrogen to our oxygen that would be collected. Question on that. Could I solve this a different way as well? The answer is probably yes, or I wouldn't have asked that question. So we could, and we could because this was at STP conditions, right? So because it's at STP conditions, you might remember a throwback from the past. 1 mole of any gas equals 22.414 liters, which means you would not necessarily have to use the ideal gas law. You could just pick it up right there, 0.175 moles of H2. And a mole would be 22.414 liters, and that should get you there as well. So because it's at STP, you could use that conversion if you remember it. If you don't remember it as normal, you could always use the ideal gas law in any conditions. But a reminder that if you want to use this, it has to be STP conditions. So you cannot use it if it's not STP conditions of 273 and 1 atmosphere. Any questions on electrolysis cells? All right, that wraps up this chapter. All right, off to the next one, I think. 19 next. We're down to 3 chapters. That's not too bad. Decent. So in this chapter, we're going to talk about transition metals, which hopefully some of it will be review for you. And then we're going to get into really the heart of the chapter, which is sort of coordination compounds and complex ions. So the reason we're going to talk a little bit about transition metals, just to remind you on some of the properties of transition metals, is a lot of coordination compounds which contain complex ions. A lot of the metals involved are transition metals. So we're going to kind of cover some of that stuff up front. So let's get into all that wonderful things that you remember. We'll start with effective nuclear charge. Anyone? Yes. All right. So effective nuclear charge, which is Z effective, is the Cliff Note version. Is let's change the slide and you don't have to worry about it. What we talk about when we talk about effective nuclear charge is really the charge that electrons feel from the nucleus based on the idea of what is referred to as shielding. So let's just take our friend lithium, for example. That is a 1s2, 2s1. I'm throwing out all kinds of old stuff here now. That is electron configuration, I think, right? So it has 3 electrons, which means when we look at lithium, it's got like a +3 charge happening there in the nucleus. It also has some core electrons here, right, which are the lower energy ones. These are core electrons. Closest to the nucleus, right? These are valence electrons, right? Which are further away from the nucleus and not held as tightly. Electrons are up there on top. Number of valence electrons, right, could be easily found by looking at the what on the periodic table? It is the valence electrons is equal to the group number on the periodic table. So everybody group 1, like lithium, would have 1 valence electron, right? 2 and so forth all the way across. So when we look at, we have 2 electrons in that first principal quantum number. I know I just like to say those big words, you know, it sounds fun. So these are our core electrons hanging out. And, you know, back there, obviously, they're not going around in circles, but we'll just draw them like this. This is our valence electrons sort of out here. So the idea of effective nuclear charge is pretty much this. When we look at the electrons here on the lower energy level, they're pretty much right near the nucleus, which means that they're going to feel the full brunt, right, of that positive charge from the nucleus, right? And when we have electrostatic attraction, positive and negative charge that come together, the strength of that attraction does increase with the size of the charge. So things that are, say, a +3 charge and a -3 charge that are hooked together will be bonded together stronger than, say, something with a +1 and a -1 when they come together. So as sort of the charge increases, so does the strength of that. So these guys here up front there are pretty much locked into the positive charge there of the nucleus. But what happens when we look at sort of our lonely electron out there by itself, our valence electron, is it is not going to feel that full brunt of the +3 charge because of an idea known as shielding. And shielding is occurring from these lower energy electrons, which are frankly in their way. So what happens is that outer electron actually doesn't feel the +3 charge. It feels something less than that. So you could actually calculate the Z effective by taking like the atomic number minus the number of like electrons that are sort of shielding. So in this case here, we have basically 3 minus 2 in this case, -1 charge for each of those electrons. That means that really that outer electron there that's flying around, the valence electron, is actually only feeling like a +1 attractive force to the nucleus, which is why it's not held as tightly and it's able to be removed. And that's why valence electrons, right, are the ones that are involved in bonding, because they are furthest away from the nucleus. They experience shielding, which means they are not held as tightly and easier to remove than core electrons. Core electrons are not involved in any type of bonding because, frankly, they have that full brunt of that positive charge and they're held really, really tight. Question on that there. So when we have Z effective and we look at sort of what's happening here, is we do see that it does sort of, as you go up and to the right on the periodic table. So if we look here, we have sodium, magnesium, aluminum, and silicone, which is basically going left to right on the periodic table. And we see the Z effective increases as you go to the right. That is because, as well, as you go to the right, there's more protons, right? So greater positive charge there in the nucleus and a greater Z effective. That is also why, as you go to the right on the periodic table and up, the size of everybody gets smaller as well, right? Because you have that larger positive charge. So even the outer electrons are closer to the nucleus because of that bigger positive charge. And that's what we see here when we look at the radius. It gets smaller as you go from left to right on the periodic table. And again, that is the relationship of size as well. So as we go this way, things get smaller, things get larger as we go down on the periodic table. And again, we have larger guys because the electrons aren't held as tightly as we go to the left there. And that means that they're going to be further away from the nucleus, given an overall size of the atom a little bit larger than on the right-hand side. These are the transition metals, in case you forgot. But this is between group 2 and group 3 there. These are our transition metals in this region here. Here's another picture in case you forgot just a second ago. And also we have some guys down here. When we talk about transition metals, they're the ones in terms of electron configuration, get into the D block, right? And by the way, these two groups here are the S block, yes, and P, and down here is F, right? And you could count off electron configuration from the periodic table if you know what you're doing by using the period number, and that for this is period 1, right? Period 2, period 3, and period 4. By the way, the D's start at what energy level? 3. So that's actually 3D, right? 1 behind the group, the period number as well. By the way, these are F's and they start at 4. I'll go with 4. Did that help you remember? That's good. So that's 4F there. And by the way, those guys on the bottom are, if you look at the atomic number, right, should be slapped right about there. Yes, that is technically where they go. And that is actually 2 behind the period number there. That's also why they're sometimes referred to as inner transition metals, because they actually should be put into that spot as well. It's fun review day. I like it. So transition metals show great similarities, obviously, within a period and within a vertical group on the periodic table. When they form ionic compounds, a lot of times transition metals can have multiple oxidation states, and that is something that you should be familiar with as well, just from naming, right? When we have transition metals involved in a name, we have to use a Roman numeral, right? And a Roman numeral indicates the charge on that particular metal, because it can have multiple sort of charges. They often will, which is really the subject of what we're mainly talking about in this chapter at the end here, complex ions. So they often are found in the middle of those complex ions, like we might have saw some earlier when we were talking, you know, say like something like this, you know, and you got like water attached and a bunch of waters. Obviously, aluminum is not a transition metal, but same idea here. We got kind of a metal in the middle there, attached to a bunch of other molecules, which are ligands, right? So water in this case would be what are referred to as ligands. Ligands are Lewis bases. Lewis bases are things that do what? I'm gonna go with electrons. I can also go with donate electrons. Yeah, so they actually donate electrons, Lewis bases. That is why water is a good Lewis base, because when we look at water, it is a polar molecule and it's got those electrons to donate. So remember, Lewis acid and bases are opposite of Bronsted-Lowry acid and bases in terms of accepting and donating. And when we talk about Lewis acid and bases, the easy way to remember that is like Lewis structure, so electrons, right? So it's electrons that are being donated and accepted. So in this case, a Lewis acid is something that will actually accept a pair of electrons as it's electron deficient. Here's a much better example of that. Here's our cobalt here in the middle, which is our transition metal. That's ammonia, which are Lewis bases and ligands all the way around here. Ammonia is also a very good Lewis base because, again, it is a polar molecule and it's got those pair of electrons right there that's able to be donated in this case. So you will, by the end of this chapter, be able to name this rather than just call it that thing there, that thing with a lot of pluses and stuff. So you'll be able to just say, like, you know, that's hexamine cobalt 3 ion, like it's nothing, right? And you'll just be able to name that with no problem. So we will talk about how to properly name these guys a little bit later on this chapter. And, you know, you need about that much room sometimes for the name. Like it just keeps going and going and going. All right, more fun to come later on. All right, so let's talk a little bit more about transition metals and ionic compounds. A lot of times, depending on the transition metal and really the oxidation state of the transition metal, You will see maybe some different colors of, say, solutions that may develop, even though you may have the same element involved. You may have the same element where in a certain oxidation state or with a certain ligand, it may make a blue color versus, say, a pink color or a red colored if it's another ligand or oxidation state that's sort of happening. Many of the compounds are paramagnetic. Paramagnetic means go with unpaired electrons. I could be making this stuff up. I don't know either, really. It's been a while since I taught like that first semester. Not really. I taught it like last week as well. So paramagnetic means that basically when you look at the electron configuration, you have some unpaired electrons, right? And electrons have a spin quantum number, right? The ms, which means that they're affected by electrical field. They have kind of like their own electrical field sort of happening. Diamagnetic means that all the electrons are paired, right? So they're opposite sort of spins and are paired up, right? And when we do put them into an orbital, right, they go in opposite directions, right? This has a ms plus a half, right? And that is a spin quantum number of -1/2, right? They teach quantum numbers, right, in 50. I just want to make sure they still do that. All right. So let's talk about electron configuration of these things. To write electron configuration, obviously electrons are found in orbitals, and there's a few different types. There's s orbitals, there's p orbitals, there's d orbitals, and there are f orbitals. And in certain cases, there's only one type of s orbital. There are 3 types of p orbitals. There are 5 types of d orbitals, and there's 7 types of f orbitals. And as you know, and as we just drew there a second ago, any individual orbital could hold a maximum of 2 electrons, right? Which means if you fill up in terms of electrons, the s orbital, you can put a maximum of 2. If you fill up the p, which is sometimes referred to as the subshell or sublevel, and that's all 3 of the p orbitals together, like the px, py, and pz orbitals, right? Which are those kind of figure 8s that are on different axes there in 3-dimensional space. You would have 6 electrons. If you fill up the d subshell would be 10, and the f subshell would be 14. I'm sure you remember how to write electron configuration, hopefully, but just a reminder, you can recreate the order for yourself, which I'm sure you were perhaps taught by going S's start on the first energy level, P start on the second, D start on the third, and F start on the fourth, and then frankly, just fill in the numbers underneath. So this is something, again, you could recreate pretty simply if you just remember sort of where each of those orbitals begin, and you always start up here and you just zigzag back, right? You just keep going. The major difference that people usually will screw up is right around here. The 4s is actually lower in energy, right, than the 3d orbital, which means that the 4s will actually get the electrons first, right, followed by the 3d and so forth. So when we look at V here, this is also noble gas configuration, which is you could take the noble gas that comes right before whatever you're writing, put it in brackets, and that it represents the electron configuration for that noble gas. And we have 4s2, 3d3. There are several exceptions to electron configuration, as you may also be remembering, and probably the 2 major ones that most people talk about are the chromium and the copper in terms of difference. When we look at chromium, which is like 24, you would look at 1s2, 2s2, 2p6, 3s2, 3p6. And if you just went by the sort of regular order there, you would go 4s2, 3d4. It's been found experimentally to be more stable by having an extra electron up in the d orbital, and that's able to be done because they are very close in energy, the 4s and like the 3d. So we go into the 4s first, and then we start filling the d orbitals. And copper has a very similar sort of exception. It's got one more electron up in the D, one less in the S. As you may also be familiar with, if you look at periodic table, below chromium and copper come down and like in. There's a ton of them that have exceptions very similar to that, like silver is an exception. PD has no electrons in the s orbitals or anything like that. So there's a lot of exceptions in that transition metal region in terms of where those electrons are. Most people that take something like Chem 50 use just chromium and copper that most people sort of focus in on, but there are a lot of other ones in those general region in the transition metals that also have those exceptions. As you may also remember, what happens when we start filling in electrons into the d orbitals in terms of the energy of those orbitals? They switch energy levels. So once you start filling electrons into the d orbital after the s orbital, there's actually a switch in the energy of those orbitals. And what ends up happening is the 4s actually ends up being higher in energy than, say, the 3d. And that's really important for when transition metals lose electrons. When transition metals lose electrons, the first ones they lose is the s electrons, in this case, the 4s electrons. And that's because of that kind of switch in energy that occurs. And it happens in all the transition metals. Basically, they will always lose those electrons first. And then if they need to, they will sort of go into the d orbitals at that point. So that's an important thing to remember, and it will help you when you write electron configuration a little bit later on when we talk about crystal field splitting and where electrons end up and stuff like that. Any questions on that there? So again here, when we do lose electrons in transition metals, they will lose that. So if we look at something again like iron, for example, if we look at something like iron, which is 26 there, I think. It is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6 in this case. And if we look at this part of it up to here, that again is counting the top 2, 4, 10, 12, 18 electrons, which is where the argon noble configuration comes from, 4s2, 3d6. Now, if iron was to lose 2 electrons and become a +2 charge, that means that it will only have 24 electrons. So it will again lose the s electrons first because they are actually higher in energy, and the correct configuration for iron with +2 charge would be 3d6 in this case. If iron had a +3 charge, it would have 23 electrons, which means we would still lose there. And now we would have to take one out of the D, and that would give us argon 3d5 in this case. So transition metals are a little bit different than representative metals. Representative metals, when they lose electrons, end up at a noble gas configuration. Transition metals really don't, and it's because they have a long way to go to get back to the noble gases, but they will always lose those S's first. Any questions on that there? All right, so do you have this one, or do you have a different one? Yeah. Let's do this one, why not? That is number 20-something there on the periodic table, 21, I think. Yeah, looks like a winner. All right, write the electron configuration for SC +1. You can write any way you like, yeah. And while you're at it, also we'll do the one that's on the nose. I think this is nickel +4. So why don't you write that one as well? And that's 28 is nickel, I think. All right, so the electron configuration for both of those guys. Let's see what you come up with there. Okay, so let's take a look at, so SC really with no charge is 21. So as a +1 charge, which means it lost an electron, which means really it will have 20 electrons. So again, argon would get you to 18 electrons. And then we would have technically 4 with 3D1 would be what SC would have with no charge. +1 charge is the one that we actually should get rid of. Yeah, but we still will have an S left, right? So we will have argon 4s1, 3d1 in this case. Yeah. So we do write electron configuration as maybe you were taught in terms of filling order, how the electrons go into the atom. You sometimes will see people write electron configuration based on energy, how it is at the end. But usually 99% of the time, and how you should probably do it in all your classes, is write electron configuration in the filling order, which again means the 4s should come before the 3d in this case. If we look at nickel, nickel here would be argon 4s2 and 3d8. Sounds like a winner there. So +4 would mean we would be down to 24 electrons. So we definitely need to get rid of 2 here and a couple out of there to get us 4 total. So this guy should end up with an argon 3d6 in this case, which means that guy will have 6 d electrons. Question on electron configuration. You do need to obviously know how to write it, and you need to know how to figure out how many electrons it has, d electrons. That'll be really important for later on in this chapter. Any questions on how to do that there? Yeah. Let's talk about some other properties here of transition metals. As we talked about with oxidation numbers, they obviously can have a lot of different oxidation states. And as we played with MN in lab, right, it, as you can see, can have a ton of oxidation states. As we go down the first period there, it sort of increases as we get to MN, kind of comes back down. But a vast majority of them will have a +2, +3 is very common, which is those guys in red is the common oxidation states. But again, depending on the situation, like something like MN can have multiple types of oxidation states that can happen. Ionization energy is the energy required to remove an electron, right, from the gas phase. And that is basically when we remove electrons, we make cations as a result of that, right, which are positively charged ions. And when we do remove electrons, they are removed just like kind of hydrogens come off. They actually are removed one at a time, so they don't all just drop off. So for example, if we take our friend magnesium, the first thing that would happen is magnesium would lose 1 electron, and that would be the first ionization energy associated with that, the energy required to remove that electron. The next thing that would happen is magnesium would then dump a second electron, and that would be the second ionization energy. And maybe it will try to dump a third electron here, and that would be the third ionization energy, as I read above there. And first off, is it easier to remove the first electron? Second, which one's easier? First one is much easier to remove because as you remove the first electron, the overall size of that ion gets smaller, right? Because it lost some electron density. That means the remaining electrons have now moved much closer to the nucleus, right? And is going to be held tighter. And it takes a lot more energy to remove it. And obviously, as you keep removing it, it gets smaller and smaller and harder to remove. So the general pattern in ionization energy is there's 2 sort of patterns. There's just the first ionization energy pattern, which is when you just look at the first ionization energy, it increases as you go this way up and to the right and decreases as you go down. And that is why when we go up to the right, that is non-metal area, right? And those guys typically don't lose electrons. So they have very high ionization energy, which means they like to hang on to their electrons. Left and down are metals, which are typically the ones that will lose electrons. So they have lower ionization energy. The other pattern that we see is as you go from the first ionization energy to the second to the third and so forth, you will see the energy increase to continuously try to remove those electrons because it gets harder and harder. That's also why when we look at something like magnesium, to remove that first electron, it's like 735 kilojoules, kind of doubles almost there to remove that second electron. And by the time we get into that third electron, that is like almost a 7-fold increase in terms of energy. And that usually doesn't happen for something like magnesium, because by the time we get to the third electron, what type of electron is that? That is its core electrons, yeah, because magnesium's group number 2, it only has 2 valence electrons, which are these guys. This guy is like the core electron you're trying to remove. Doesn't really happen, which is why we know magnesium is a +2 and stops at that point, because energy-wise it is not efficient for that to happen. Same thing here with sodium. As we go from the first electron to the second, it's like a 10-fold jump in energy. And that's why sodium will only lose its 1 valence electron. It's not energy possible normal conditions for it to pop off that second electron. And that's why sodium has a fixed charge of +1. So this is also why certain things have fixed positive charges, like in group 1, group 2, and like aluminum, because once it gets to those core electrons, there's no chance that those electrons are going to be popped up because it's not energy efficient to do so. Any questions on that there? Here's obviously all the stuff that you should know about the transition metals. I don't think so. There's our atomic number that's increasing, our electron configuration. You probably know most of those. We do see, as we go to the left to right there, a decrease in the size, as we talked about. These are our first, second, and third. So we see an increase in ionization energy as we go from one electron to the next. And we also see overall it gets higher as you go to the right, the first ionization energy. There's our reduction potential, and also our common oxidation stage, which mostly are 2s and 3s as you go across as well. Here's some dots of the first versus the third. And again, you can see the third is much higher than the first ionization energy. So much more energy required to remove the third versus the first electron. Here's including the second, in case you felt bad that the second ionization was on the first graph. Here it is right there, and it's in the middle as we would expect it. Electron affinity is the energy change that occurs when an atom gains an electron. And when something gains an electron, we usually associate this with the formation of anions. And those are guys that gain electrons. And the general trend when you look at electron affinity is it does increase as you go up and to the right and decrease as you go down to the left. It's not a perfect sort of trend, but it pretty much generally that trend. If we look here at the energy change within group 7, it does increase as you go up, but then it kind of goes back down. So it's not a perfect sort of pattern, but that is what we typically see. If you have an electron affinity or an affinity for something, you usually like it, right? Which means these are things that like to gain electrons, right? Is electron affinity and electronegativity the same thing? It is not. Electronegativity, which is often confused with this, right, is the ability of an atom to gain electrons, right, or bring electrons towards itself, I guess is a better way of saying that. And that also increases as you go up and to the right on the periodic table. Which element is the most electronegative? It is fluorine, right? It's the most electronegative. So electronegativity follows a very similar pattern, but it is different. That's the ability to bring electrons towards itself. Electron affinity, again, is more of an energy change that occurs when it actually does gain that electron and becomes an anion in that case. More things there. These are relative reducing ability of first row transition metals. And we have our potential here. And what we see here is reducing ability increases as you go up, which means if the reducing ability increases, then this guy should be getting oxidized, right? Because our reducing agent is the guy that gets oxidized. So here we would see SC has a 2.08 potential, and our copper there is minus 0.34. And you may be saying to yourself, isn't the more positive one the one that should be the cathode and get reduced? You would be right. It is, as we talked about, the one that is more positive should be the cathode and get reduced. Why is that not the case here? Or is it the case here? It actually is the case here. These are all written as what type of reactions? They are. And what type of half reactions? Oxidation or reduction? These are all oxidation reactions, right? What we're used to think about in terms of being more positive is your cathode is reduction reaction, right? Which means if we flip these reactions all around the other way, that means this becomes negative, 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 and positive, which means the one that we would expect to be the cathode is actually the one that's on the bottom there, right? And so these are what sometimes referred to as SOPs, standard oxidation potential, right? Because these are all written as oxidation reactions rather than our reduction reactions, which we normally think of. So if we kind of turn these into our SRP, then that would make sense that this guy would be more our cathode versus our anode in this case. Any questions on that there? I guess I guessed copper right this morning. Was that 0.34? That's pretty good. All right, that's good. I just threw a number up there, hope that would stick. That's good. All right, so here's our size difference that we talked about as well. Here's what the first row transition metals look like, in case you pick them out in a lineup, I suppose, right? This is stuff that really doesn't relate to you anymore. So we're just going to kind of do that, do that, do that, do that. Just we don't do those experiments anymore, so it's not really important. All right, so coordination compounds. This is really the heart of the chapter. That was, again, just sort of a review, a reminder of some of the background of these things, because they will be sort of touched upon here as we go through this. So a coordination compound basically will consist of two things. It will consist of a complex ion, and it will also consist of a counter ion. So you could think of a coordination compound like an ionic compound. An ionic compound, right, has a positive cation, right, and a negative anion. And when we write formulas, right, it's always the positive guy first, right, and the negative guy second, and that's how we name them as well. So coordination compounds will contain a complex ion and a counter ion. And in terms of charges, you can really have any charge in a sense. And what I mean by that is you will have your complex ion and you will have your counter ion. And if your complex ion is positive, you will have a negative counter ion. And if your complex ion is negative, you will have a positive counter ion. The idea of the counter ion is to balance it out, really like an ionic compound, to kind of zero overall charge. So a complex ion is, as we've been talking about here, a metal, usually a transition metal there in the middle, and attached to it a bunch of ligands, which are Lewis bases and are guys that will donate a pair of electrons to our metal. Our metal, which has a positive charge, and the only way to get a positive charge is to lose electrons, right? And that means that really, in this case, our metal is electron deficient and is our Lewis acid, right? So you could think of these sort of interactions of complex ions as really a Lewis acid and base situation that's occurring. The metal, which is deficient in electrons, will accept the electrons from our Lewis bases, and it's really that sort of situation that's happening here in our complex ions. A ligand, again, which is a Lewis base, usually to be a pretty good ligand, polars being good and having some lone pair electrons or dots, right, when you draw the Lewis structure on them. So here, water is polar, and it has those electrons on the oxygen. Same thing with ammonia is polar. The other way, right, is things that have negative charges. The only way to become negatively charged is you had to gain some electrons along the way, which means you have some extra electrons to give. So they make really good sort of ligands. Now, when we talk about a ligand, they do have certain donor atoms that are attached. And the donor atoms are really where those electrons are going to be sort of donated from. And that will give us what is referred to as the coordination number. And the coordination number is how many atoms are directly attached to the metal in a complex ion. Now, the coordination number is not necessarily always the number of ligands that are attached, and that is because of something we talked about earlier, and we'll talk about it again here. The ligands themselves can be different. There are certain ligands that are what are referred to as being monodentate, which means that they will bond basically one atom per molecule, like oxygen. When you throw an oxygen in there, it is just the oxygen that's going to bind in. Same thing with the nitrogen here on ammonia. Those are monodentate. There are certain ones that are bidentate. Ethyl endyl diamine, which is oftentimes abbreviated as EN. So you'll see EN abbreviated a lot. It is a bidentate sort of ligand, and it looks something like this. Dare I give it a try? We'll go that there. It's feeling very organic here. Like that. All right, so that's ethyl endyl diamine, I think. Looks like this. And when a metal is involved, each of those nitrogens will bind to that metal, and that means you get a 2-for-1 deal on it. Not bad. So for every one of those molecules that come in, you get basically 2 attachment points, which means every time you have one of those, the coordination number goes up by 2 for every one that you have. We talked about, I think earlier, briefly about oxalate, which is another one. Oxalate is C2O42 minus. It looks like this. It's got the dots there and there. So when you have something like oxalate, which is also bidentate, the single bonded oxygen will each bind into the metal. And again, you get the same sort of 2-for-1 deal. And for every molecule of oxalate, you get like a double shot on the coordination number. So if you had something like, say, this, the coordination number of this guy would be, it would be 4, because each of these are going to bind twice, and there's 2 of them. So it won't always be that number that is there on the bottom, as opposed to if you had coordination number of this guy would be 6, as water will only bind once through the oxygen, and there's 6 of them. So when you're asked about coordination number, sometimes you're only given the formula, and very common people just go, oh, it's the number, but it may not always be the number depending on the ligand that's present. EDTA, which is a big name, and we'll talk about that name next time and see it, but it is actually a polydentate. For every molecule of EDTA, for example, there are 6 places where it will attach to a metal. And that's why EDTA is used to tie up metals and things, because pretty much for every one of them you throw in there, it's just going to surround the metal basically and tie it up in 6 different locations. Any questions on that there? All right, seems like a good place to